Okay, continuing with section 6.1, I was explaining the pictures that were up at the top. And in those pictures, the pictures that were at the top of the first couple of pages of 6.1, and I was at the top of page 2 on the theorem page. I was looking specifically at this picture right here. I had already discussed these two in the last video. And here you are rotating through quadrant 1, through quadrant 2, through quadrant 3, and you're stopping right here, right on an axis. This has a particular name. When you land in midair like this, you'll have the ability to draw a triangle. When you land in midair here, when I say in midair, I mean in between two axes, you'll be able to draw a triangle. Here, when you're landing right on an axis, let's say somebody tells you to go 90, then another 90, then another 90. You're landing right on an axis, and we call that a quadrantal angle. When you rotate so much that you either land on the y-axis at 90 degrees or the negative x-axis at 180, or you land on 270, because each of these is 90 degrees, each quadrant. Those are called quadrantal angles. You won't be able to draw a triangle in that case, but you still will be able to identify an x and a y coordinate, which is what it takes to do all the problems in 6.2. And, we're just getting familiar with moving around the circle. That's all these pictures are about. So I just wanted to remind you about what it means to talk about quadrants that are numbered. Here was a picture of a terminal side in quadrant 2, one in quadrant 4. This one wasn't in any quadrant at all. It's actually just in between quadrant 3 and 4. Yes, you could say it belongs to both of them, but not a specific quadrant. Here we come up with some names that you may be familiar with, but need to refresh you on all of these. So let's say that you go one entire trip around your circle. Mathematically, there are different names for that. If your rotating arm rotates all the way until it lands right back where it started on, that's why you only see one arm here. There really are two rays, but this rotated full 360, and so it's right back where it started. You could say that the rotation was one full revolution. You could also say that it was 360. Now we're referring to this angle in a positive sense because it rotated in a counterclockwise fashion. Or you could say that it rotated, in case you don't remember this, from here to here is called 1 pi. When you go all the way around the circle, that's called 2 pi. So there are 3 different ways to say that you went all the way around a circle, that your terminal side rotated clear around the circle right back to where it began. And that would be to refer to it as a revolution, 360, or 2 pi. Depends what language you're being asked to speak in. You're speaking in words here, you're speaking in degrees here, you're speaking in what's called radians. Radians is just a fancy name for decimal type numbers. I think you're all familiar with the fact that pi is a decimal number. It's approximately 3.14. This is approximately 6.28. This is 2 times pi. And this is just the symbol that stands for it, because it's actually a decimal that runs on and on and on. Okay, sometimes you start off with your 2 rays like this, and the terminal side rotates until it is completely perpendicular. So if we wanted to speak about this rotation, this angle in different ways, we will speak of it in a positive sense because that's a counterclockwise rotation. So we could call it positive 90. We could call it a right angle if we want to speak in words, or if we want to speak with regard to revolutions, an entire revolution is 360. 90 would only be 1/4 of that. So a quarter revolution is the same thing as 90 degrees. In this picture right here, this would be a 180 degree. Again, we'll speak of it in a positive sense because it's the rotation of the terminal side was counterclockwise, vertex still right there at the center. And you could speak of this as a straight angle because it it's in order to, if you were on this straight line right here, if you rose up off the line and then landed right back on that same straight line, you would have this arc of 180 degrees. Therefore, in geometry as well as any math class, this is referred to as a straight angle because it's all part of the same straight line. You could also say it's half of a revolution. Remember, whole revolution's 180. So half a revolution is, a whole revolution's 360. Sorry about that. So half a revolution's 180. Okay, moving on to the problems that actually go with this. See, it'll tell you you've had enough background now, so stop and do problems 1 through 3. So let's start with the problems. When I print off these homework problems right from my math lab, even though it's called My Lab Math, I'm not used to saying it like that. If the multiple choices that you're being given are pictures, it's only going to capture 2 of them. When you try to print this in landscape version, it comes out even more horrible. So I'm capturing the problems like this. So for the very few multiple choice problems that you do have, it's only going to capture 2 pictures. That doesn't stop you from doing the problem though. You can still do the problem. These homework outlines come with all the answers. When you print them, you'll see the last couple of pages are the answers that go with the problems. So you can draw it out as you expect to have to draw it out. Realize that, when you take a test with me, you're going to be drawing it out freehand anyway. You're probably not going to have that many multiple choice questions. So you should be able to do that. And if the answer we want is here, it's here. And if not, then we know it's one of the ones that got cut off. So here we go, drawing. Okay, I'm going to do an X and a Y axis just so we have something to refer to. I'm going to keep one arm fixated at the X axis and I'm going to let the other one spin. And I'm going to show the spin by way of, you can use these dotted lines like they do. You can use another little arrow. Whenever your other arm is spinning negatively, that means you're going this way. So you're going that way. You can draw the little arrow there if you want, but it's not necessary. They don't do it. And you're going to stop right when you've gotten to 90 degrees, but this would be considered negative 90 degrees. Okay, so that's the picture that goes with it. I don't see that here. This has nothing. This went this way, but too far. It didn't even... it went way past where it needed to go. We just needed to stop right there. So this picture must have gotten cut off. That would be what the picture looks like. When you're in my math lab, you're going to see all 4 pictures. So no matter, every time you're doing a multiple choice problem, do it first the way you see fit to do the answer, as though you have no multiple choices to select from. Then go and look at the choices, because looking at the choices first can sometimes make you think about certain things in the problem incorrectly. In problem number 2, you're actually being asked to do the same exact problem, because we were talking about on some previous pages that 1 pi from here to here is also called 180. So this is really 180. There's a negative in front of it, divided by 2, and that's nothing more than what you just did. We already discussed what the picture looks like when you rotate to negative 90. The 2 arms start here. One arm rotates until it's down 90 degrees. So in this problem, the picture did not get cut off. That would be the same picture that we just created in problem number 1, because they were asking the same question. They were just trying to see if you understood that you're being asked the same question. Right, so that's an angle in degrees. The second one, they gave it to you in radians, but the picture is the same. Okay, here you have to start understanding how to think about this circle in terms of fractions. That is going to be very, very heavy in this class, so I might as well start talking about it now. When you talk about what we call landmark locations, these are 2 of the landmark locations that are very important. I mean, this is important also. This is half of a pi. This is 1 whole pi. This is 2 whole pi. So this is 1 half, 2 halves, 3 halves, if you want to talk in halves. But let's get our thinking right now, just because I don't want to confuse you with halves and fourths. This problem happens to be in fourths. They're giving you an angle in fourths. So if you want to be able to count in fourths and land in the proper quadrant with your picture, because you do have to pick a picture that goes with 11 fourths, then you have to have the skill of being able to give these two landmark locations names that have to do with fourths. Like, for instance, this is 1 pi. Another way to write 1 is any number over itself. So 1 pi is the same thing as 4 fourths. Another way to write 2 when you're talking fourths is just double the number at the top. 8 over 4 would be 2. So instead of 2 pi, you could call this 8 fourths. And when you have your picture in the same denominator as what they're talking about, then it becomes pretty easy to rotate around the circle successfully. So like, for instance, you're going to go full revolution to get that 8 pi, to get that 8 fourths, but you need to go as far as 11 fourths. So not only do you have to go to 8 fourths, but you have to continue moving. So now we're going to continue moving even beyond the 8 fourths. So this is going to be 1 fourth, 2 fourths, 3 fourths. And that kind of makes sense that if we're going beyond 8 fourths, how many extra do we need? We need 9 fourths, 10 fourths, 11 fourths. We need 3 more fourths to get to 11 fourths. And that's what this little extra is. 1 fourth, 2 fourths, 3 fourths. And if I would have gone all the way there, I would have been another 4 fourths, which would have been too far. And draw that terminal side. So where this terminal side stopped, that represents 11 pi over 4. Okay, moving on. Now we're going to learn how to convert. So before you learn how to convert this next problem, you need to know what are the ratios that I have, the conversion ratios that I have. Because whether you're converting in biology, physics, math class, converting is done by way of what we call a conversion ratio. It's just a fraction. And you can flip that fraction right side up or upside down, depending on what you're converting into. So the next thing for us to look at is, what are those ratios that we're going to use to convert? So that would be the next page of your theorems page. Let me find that. Okay, so that's this page right here. The next page in the theorems page talks about converting between degrees and radians. So all you're going to do is use this conversion ratio right here. 1 pi over 180. I kind of wrote on that a little bit, but let me erase it so you can see it better. It's 1 pi over 180, or you can flip it over and use it like this, 180 over pi. What you do have to learn here, and what some students get confused about, is the unit that you're being asked to convert into. Like this says, when you want to convert into radians. When you're moving into radians, you want radians at the top. Remember, radians just means it's a fancy word for decimals, and pi is a decimal. So this would mean that you have radians at the top. If you're being asked to convert into degrees, then you want to use this conversion fraction, this ratio, like this. Just take it and flip it over. So what you want to convert into, that type of unit should be at the top. Okay, so some examples that would go with that would be, for instance, number 4, and I'm going to get cut off here in a minute, but I'll try to get through this problem. So if you were going to do 105 degrees, you would put your conversion fraction right here. You're trying to go into radians. So radians goes at the top, whereas the 180 goes at the bottom. And what would happen in this particular problem is that the degrees are going to cancel and you're going to completely be in radians. You're just going to, and I'll finish